Thank you. Hello, everyone. Thanks for coming today. Let's start. A few words about myself as a start. I've been researching x86 platform security for quite a long time. This work covers subjects like Intel Management Engine, Intel BootGuard, and UEFI biosecurity. Today we're going to talk about issues in low-level architecture components like authenticated code models. I will be calling them ACMs. And the microcode, we'll see how these issues can be discovered and exploited. And then we'll talk about possible mitigations for such an attack surface. Let's go on. Let's start with the CPU roots of trust overview. Every modern Intel CPU has processor cores with the bootstrap processor, which starts powering on, which starts when powering on, and this core begins executing the start instructions in the firmware. The other cores, called application processors, they are started by the bootstrap processor when ready and needed. An optional graphics core, this is another component. The other one is integrated memory controller, level 3 cache. This is very important for us today. It is shared between the cores and some other input-output logic. There is a read-only memory containing the CPU microcode inside each CPU core. The microcode is programmed while manufacturing the device. This is our first root of trust for now. Control unit, after each powering on, loads the microcode into a faster and rewritable type of memory called control store. So what is a microcode? Public sources tell us that this is a program written in hardware-level instructions to implement a higher-level instructions. So you can see MoveS instruction implementation here on the screen, for example. The thing is, and it is well known for years, that the microcode can have bugs, vulnerabilities. These can be security issues or performance issues, so it should be updatable. Remember, the original microcode is stored into the CPU, inside the CPU, in a non-updatable memory. Hence, the updated version of microcode should be replaced in a control store every time CPU is powered on. And you can notice such updates are included often in system firmware. You can see on the screen. Here's a table pointing to the microcode updates. We'll talk about this table a bit later. Please note that these updates are CPU model specific. So, about the table. This is the firmware interface table. Obviously, it is a part of system firmware stored in onto the SPI flash memory. You can see a common image structure here. There is a pointer at the end of the BIOS region pointing to a firmware interface table. This is how the modern Intel CPU finds it and loads the microcode updates in an automatized way before executing the BIOS. What else do you know about FIT? It had started to be a required element for Intel architecture since introduction of Intel BootGuard technology. Because it contains entries to point to BootGuard components. Please see other entries of it on the picture. This allows the CPU to verify the integrity of the BIOS code before executing it. Also, like I told before, firmware interface table is used to update the CPU microcode before running any firmware and before starting even the Intel boot guard. So let's see what a microcode update binary looks like. It starts with the main header containing such fields like version, data, not data, the date, build date, CPU model code. Here it's called a processor signature, checksum of the header, and etc. Bless you. This this header is followed by an extended header. Let's look at it also. This is an extended header structure. Seems like a common Intel signed binary structure. It is also used for ACMs. We'll talk about that later. And it is used also for Intel CSME firmware. It also has fields like version, sizes, processor signature, security version number to deprecate loading the downgraded versions of microcode once given version is loaded, of course. Also, this header has an RSA public key and signature allowing to authenticate this update. So the CPU will verify the integrity of the microcode before loading it. That doesn't allow us to modify the update. After the headers, the hash of the public key is hard-coded into the CPU, and based on my observations, it can stay the same for a few CPU generations, and even for production and pre-production, I mean debug versions of platforms. The microcode update body is unfortunately encrypted. This is also why you cannot change the microcode. And that's why almost no one actually knows what else the microcode is capable of, besides some startup behavior like microcode updates, loading, or Intel boot guard implementation. However, here are some collection of facts about the microcode actions. Like was told before, it implements CPU instructions. It configures the execution logic on the line. That's how bugs like side channels are fixed. It implements some startup behavior, like firmware interface table parsing. This is how it can load microcode updates from firmware interface table. And it loads and executes Intel authenticated code modules. They can be executed, they can be pointed by the firmware interface table or some other ways. It depends on the ACM type. So a few words about these ACMs. They are signed and sometimes encrypted. They have a similar structure like you saw before. I mean the header. They are loaded into a shared level 3 cache. I guess it is because the DRAM is not trusted, and sometimes when ACM is executing, the DRAM is not available at all. Some public sources mention this cache memory for running ACM. They mention it as AC RAM, Authenticated Code RAM. This module is executed only from there and only by the bootstrap processor. Other cores should be sleeping at this moment. They obviously serve as a root of trust and as an implementation support for such technologies like Intel Boot Guard, Intel Trusted Execution Technology, and Intel BIOS Guard. This is also known as platform flash armoring technology. So now we can see all CPU roots of trust in a single UEFI BIOS image. You can see firmware interface table, microcode updates, file and all of the ACMs I mentioned before. So now let's talk about the ACM for the earliest platform boot state, for boot phase, Intel Boot Guard ACM. And let's talk about its issues. As you can see on the picture, the blue area is protected by Intel Boot Guard. The ACM verifies its integrity. So in case you somehow manage to modify the system firmware, making changes to this blue area will end up in the system refusing to boot. It will be bricked. However, the firmware interface stable, microcode updates, and this ACM itself are placed in an unprotected area in most of the systems. So we can replace them with older versions. And the question is, what can be achieved that way? To find this out, let's look at the ACM header format. We have already saw something similar today in the microcode header structure. The chipset ID field, which I don't know why, but it is always 0. The build date, the security version number, and an RSI signature. Obviously, it is for authentication of ACM. What do you know at the moment? Intel Boot Guard ACM is a 32 kilobytes binary. The hash of RSA public key is used to verify the signature, and is used to verify the public key, and it is locked into a microcode. This should protect from running older versions of ACMs on the newer CPUs. Security version number also should protect from downgrading the ACM. This is how it should work, and this is the reality. The key for the signature verification hasn't changed for years. Today, in 2020, 2020, yes. they use the same key for signing the ACM as did since introduction of Skylake architecture. You can say they have the security version number for protecting to block the downgrading the ACM. However, I will say, here's the reality. This number, this value, it changes very infrequently. A few ACM versions in a row can have security fixes applied, but without increasing the security version number. Binary diffing helps perfectly to reveal the patches. And here's one I found in the versions, signed with the same key and having the same security version number. Here's a 2016 version of Intel Boot Guard ACM. You probably know this ACM should verify 2 key manifests describing the integrity of UEFI BIOS image and describing the structure of UEFI BIOS image. And here's the code parsing the first key manifest. And at the end, an RSA signature checking routine is invoked. Let's look into it. There was an issue in this routine. An RSA public key module on the next key manifest is verified, but the public RSA exponent is not. This obviously allowed performing cryptanalysis attacks on RSA signature by replacing this public exponent with a small value. And in 2017, that was fixed. They added a flag while invoking this routine, and in case this flag is set to true, both of RSA public key modules and the exponent will be verified. So after fixing these issues, they haven't changed nor the SVN security version number, neither the signing key. This opens a way to replace the ACM with the vulnerable 2016 version and to attack Intel bootguard verification procedure. The next interesting case is downgrading Intel TXT ACM. However, since this is not a startup ACM like the bootguard ACM, it is not pointed by the firmware interface table. This attack should be done in a runtime. To do that, firstly, let's see how the CPU could be tricked to downgrade the microcode, because this is an important step. We'll see it later. What do you know about the microcode updates? They are to improve stability, performance, and apply security issues. It is a very important note. Updates should be loaded onto each time CPU is powered on. I mean, after sleep, hibernation, or full shutdown mode. I've been watching that far not always updates are loaded by the CPU from the firmware interface table. This is because if the update requires something special like initialized DRAM memory or which is not available while firmware interface table is parsed, it has to be loaded by the BIOS manually, I mean in a legacy way, as early as possible from the moment conditions are satisfied. Also, probably the firmware interface table is not always parsed while leaving sleep or hibernation modes. It might be performance optimizations. This is why you can always find a microcode update loader in the modern BIOS. And here's another very important notice. Updates should be loaded onto each core separately. This is the legacy update microcode update loader. It looks like this. It uses an MSR BIOS update trigger to update an input microcode binary pointed by the CPU RX register. To check the CPU update version, the BIOS sign ID MSR is used. Besides the above set, what BIOS does to load the microcode update? Firstly, the CPU PIE model finds the appropriate update, one of the most actual and supported by the installed CPU, because the microcode is a model-specific thing. Secondly, it copies the update from the mapped SPI flash memory into a physical memory. The physical address of the update is stored into a handoff block. This is just a UEFI BIOS specific data structure, never mind. And a bit later, the platform init module will find this hop, retrieve the microcode update buffer address, and start a microcode update loader to apply this update. Please note that all of these actions are performed during the normal boot path. What else can be done? Later, the system management mode code also finds this hop and retrieves the microcode update saved address and copies the applied update into system management RAM to protect it from being replaced or damaged by an operating system. And finally, the SMRAM address of the applied microcode update is stored into a UEFI variable called int ucode. An interesting notice here is that this variable is accessible both from the boot time environment and the runtime environment, meaning it can be fully accessed from an operating system. As you can see, these actions are performed to optimize performance for waking from sleep mode. In other words, after the system was put into sleep mode and when waking up, the CPU PIE model, instead of searching for that microcode update again in the firmware interface table, it gets the pointer from this UEFI variable int ucode, and then it saves it into a hop. And then the update operation repeats. The platform init model finds this hop, retrieves the microcode update address, and updates the microcode with it. And here is an obvious way to perform a downgrade attack. We can load an old microcode update image into a physical memory. We can make the int ucode UEFI variable to point it. And then we should perform a sleep-wake-up cycle. The system will be booted up with an attacker-provided microcode, if it is valid and pass the integrity check, of course. And here's the RW everything screenshots. The 2019 version of the microcode update loaded, and after performing the above said actions, the 2018 version is actual for the CPU now. There are a few consequences of this attack. The first and the obvious one is removing fixes for side channel attacks. This could open ways for researching. But if we talk about security incidents, most of them are extremely hard to perform in the wild and have never been spotted. However, there's not much of available detection tools for side channel attacks. If you still want to know more about it, please refer to this detailed analysis I linked. Also, I've noticed that Intel introduces a new memory type against speculative side channel attacks. This is a very interesting paper. I would recommend it to read. Another interesting case is to unlock platform debugging capabilities. My experience showed that some downgraded versions of microcode has no anti-debug mitigations, and such as the mentioned vulnerability. So this technique could be useful for those who wish to use the dynamic analysis in platform security research. And the good part is that ACM authentication is performed by a microcode, like I told before. Probably the microcode is directly binded with the specific ACMs versions. I mean the runtime ACMs like TXT or the BIOS guard ACMs. The microcode update might know the hash to verify the public key of the ACM or the security version number of ACM. Anyway, the older versions of microcode supports, in other words, does not deprecate loading of old versions of ICMs, which is also the updatable firmware component and can have security issues. Hence, downgrading the microcode allows to load the downgraded versions of ACMs with with an exploitable one-day vulnerabilities. This obviously compromises the technology dependent on the ACM. And well, again, we'll start with the Intel bootguard ACM. It is not encrypted, as you can see. The binary diffing is applicable to find 1 days in it. In these images, it executed only on startup before the BIOS, when CPU is powered on and released from the reset state. ACM does not verify BIOS when waking from sleep mode. This is because of performance optimizations, except H12 boot. That's why in this case the bootguard ACM is not. We won't be focusing on it. Now the Intel BIOS guard ACM. This ACM is encrypted. It is extremely hard to find a fixed issue in it. This requires a lot of time for testing its behavior. And since this is a huge subject, we won't be talking about it today. And now about the Intel Trusted Execution Technology ACM. The ACNet ACM is the target here. It is not encrypted. The patched vulnerabilities also can be found via binary diffing. This ACM is triggered via getsec instruction from BIOS or operating system to measure boot chain components. Address of this ACM is specified in EBX register. And this address doesn't change from boot to boot. So downgrade is also possible by replacing just by replacing the ACM in memory. And regarding the vulnerabilities, there were a few buffer overflows that were fixed by Intel sometime in the past, and they are all almost the same. So the full attack scheme will be looking like this. We'll replace microcode in memory, replace the txt ACM, and then we make the int ucode variable to point to the old version of microcode update. Then sleep the system and reboot and wake up. However, there is a problem. The txt ACM has also a security version number, and to bypass this check, we have to rewrite the ACM while waking up from the sleep mode. Here, the S3 boot script will help us to do that. The boot script is a table of operation codes which should be performed while waking from sleep mode to restore the platform configuration in a faster way. This should be done instead of running the normal boot path. Again, performance optimizations. And there is a perfect system management mode code vulnerability allowing to modify the S3 boot script. Actually, the vulnerable model SMM PCIe SATA controller model, it has a perfect interface for making changes to the boot script from the operating system. It parses an input data from a caller, and then in a loop, let's take a look into it. Then it will take some data from this input data and place it into a boot script. As you can see here, we can add PCI configuration write instructions and a memory write instructions. This allows to build a part of S3 boot script that will change, in other words, rewrite the memory from sleep boot path, waking up boot path, and this allowed to replace a txt ACM in memory just in time before the check, before the security version number check, this is the way to attack the txt ACM. Let's talk about mitigations of such an attacks. A few times I heard that the Intel SGX software guard extensions can protect from these attacks. Well, I can say that the first part of the presentation I was talking about the boot guard ACM downgrading, and from this type of attack, yes, the SGX can protect. But the SGX doesn't check the microcode security version number when leaving the sleep mode. That's why it won't protect from attacking the txt ACM. So that's why for the first step of attack, I can suggest that Intel should better use of its security version number values. Also, another vulnerable weak point was the modification of in microcode UEFI variable. It now in UEFI bias images it marked as read-only, and it is closed from runtime access. But this is still could be bypassed if an attacker manages to run an arbitrary code in SMM and trigger SPI flash write operations on the NVRAM. Also, another mitigation is to make an operating system to update the microcode to the latest version manually after booting, but this process could be already compromised at the moment of validating the update version. So the best thing is for vendors, for system manufacturers, is to supply only the updates which could be the microcode updates which could be loaded from the firmware interface table, and always supply the most up-to-date binaries. So, so during this talk, we saw a few supply chain problems. We saw that that a small problem in a basic component will compromise all above the stack technologies it serves as a root of trust, like the boot guard or TXT. Since this is an extremely undocumented technologies, the full impact is yet to discover. So I would like to thank you for coming today, for listening. If you have any questions, you can ask now or catch me later at the conference. Thank you.